black and 255 was white. So how do we do this? Well, the mistake is saying that 0 is black. Okay? We're going to say, look, we'll map some minimum value to black, some maximum value to white, and we'll distribute them in between. In particular, 0 should be what color? What color do you think 0 should be between black and white? What comes between black and white in the universe? Gray. All right? So let's suppose we have values that go from minus 20 to plus 20 in our image. Well, we could make minus 20 black, plus 20 white, and 0 would be gray. And if we did that, it would look like this. So here we're showing you images of Gaussian noise. Just the noise. So if there's a very small sigma, so remember sigma's up here, so a very small sigma, all right, you can barely see that this is anything but a constant gray. As we let sigma get bigger and bigger and bigger, you start to see more and more speckle. And that's the effect of sigma, so it's just a noise function being added to an image. So Arpin likes these quizzes, so here we have a quiz, and if you can't do this with 3 eyes closed, I don't know. It says, look, there are 4 different sigmas here. What are those sigmas? Well, they're 2, 8, 32, and 64. Can you label them for me? 2, small, okay, right there. See, except oh, by the way, the reason we're using all these slides, my handwriting is awful. So you are going to be very happy that we have all these slides. So that's 2, let's see, I guess the 8 is over here, the 32, yeah, I guess the one on the top left is less, and 64 is there. Okay, I passed my quiz. I hope you did too.
Given an image IMG, you know that its size is size of IMG, and you can generate a noise image of the same size by passing this to rand_n. The values in this noise image will be normally distributed around 0 with standard deviation of 1. What happens when you multiply each of these generated values by 2? How does this affect the resulting distribution? Does it increase the counts? Does it increase the spread? Or both? Mark the right answer. The correct answer is that it only increases the spread. Note that we are only multiplying the values. The number of values, or their counts, are unchanged. Multiplying a set of normally distributed numbers by a value effectively changes the standard deviation of the distribution they were drawn from. Now, why is this important to know? Remember that rand_n generates values with standard deviation 1, whereas the images we've been using are of type uint8 and range from 0 to 255. What do you think happens when you add the results of rand_n directly to an image? Let's find out. Time to use a new image. If you look carefully, you'll be able to see 3 moons and a shadow. Now we generate our noise image and add it to the original. Not really very different, is it? This is because the values that rand_n generated are really small compared to the image. Let's scale up the values. Now you can see the noise affecting the image. How about we increase this further? And more. Now it's really hard to see the moons, isn't it?
I didn't say in the previous image what the range of our pictures would tend to be. Okay? Remember I told you an image might go from 0 to 1, and that would be from the darkest black to the brightest white? Well, if I did that and I had a sigma of 2, you would get black and white all over the place, and yet when I go back here, sigma of 2 is just a small variation, whereas sigma of 64 was a big variation. Why? In this image, we had this notion of maybe minus 127 was black and plus 128 was white. When we talk about the amount of noise in an image in terms of the intensity, it has to be with respect to sort of what's the overall range. So another reason to use doubles in your images and to think of them as going from 0 to 1, then we can talk about a sigma of 0.1. Well, that's a tenth of sort of going from black to white. If you want to use something arbitrary like 0 to 255, you can do that. First of all, use 0.0 to 255.0, so use a floating point number. And then you're going to have to say, okay, I guess a sigma of 0.1 in one case would be a sigma of like 25 in another case, right? Because I've stretched the whole thing out. So you have to worry about the magnitude of sigma with respect to the overall range of your image. This will catch you numerous times when you go to display an image, right? Because now you have to tell the machine, okay, I've got this image. How do you want it displayed? MATLAB has a large number of ways of displaying images. If you have the IMShow function, which I think actually comes from the image processing toolbox, you can show it this way where you tell it low and high, and it will display anything with the value low or lower as black and anything higher than high as white. Okay? You can also do IMShow and just give it this empty array, and it will scale the image for you automatically. That is, it'll find the minimum value in the image and say, okay, that's going to be black. It'll find the maximum, it'll say that'll be white, and it'll scale you. There's another function called image SC for image scale. It's a much older function. It's not in the image processing toolbox, which will also display it. Don't get caught between this question of how I display an image versus how I use an image. I just finished teaching part of this course here at Georgia Tech. I had some people computing some gradients. They computed some gradients, which involves subtractions and derivatives and all that stuff. And then one guy, he normalized his picture to go from 0 to 255 before he computed with it. You would only normalize it in order to display it, not in order to compute with it. So here's a question where we start to talk about noise. When I add noise to images as an arithmetic operation, which of the things do I have to worry about? A, the speed of the addition operation. B, the magnitude of the noise compared to the range of the image. C, whether we add the noise to the image or we add the image to the noise. That is the order of the operation. Or D, none of the above. Well, I'll tell you, most of the time when I give a quiz, the answer is either all of the above or none of the above, but not really in this case. The speed of the addition operation, back in the dark ages, you had to worry about the speed of addition. Now addition is instantaneous, okay? And by the way, last time I checked, 4 plus 2 equals 2 plus 4. Addition is commutative, so we don't have to worry about whether we add the noise to the image or the image to the noise. It's kind of weird to think about start with some noise and add an image to it. Same value. But what you do have to worry about, as I said before, is the magnitude of the noise compared to the range in value of the image. So that ends our first lesson on images as functions and image processing, our first technical lesson. I hope you didn't find it too pedantic or too boring, and you'll come back for the next ones, because as we go forward, there'll be more and more cool stuff to do. I can hardly wait, and I hope you can too.
So what did you learn today? List any new concepts, terms, or commands that you picked up in this lesson, comma separated or one on each line. You can use this and similar notes throughout the course as a reminder for yourself. This also gives us a sense of how you learn and will help us improve this course.
All right, welcome back to computer vision. Last time we talked about images as functions. An image could be thought of as a function of two-dimensional position, like I of x, y, or a two-dimensional array, we'd say f of ij, row column. And sometimes I'll try to distinguish between whether I'm talking rows and columns in x and y. And we talked about how x and y are not the same as rows and columns. In fact, row is typically going down, so if we go row column, that's yx. The other thing is, and we're going to talk about this in a little bit, there's going to be this question about whether y gets bigger as you go up in an image, which is like when you learn in grade school, right? Y positive goes up. Or maybe a lot of you think of rows going down, and so we'll have to wrestle with that. And we also talked about that even though indexing in a computer world should start at 0, in MATLAB, indexing of arrays starts as 1, and you're sure to screw that up somewhere in your code, but eventually you'll learn to figure it out. All right, let's do some work. Not much work, but a little bit of work. So last time we talked about adding a noise function to an image function. So here we have our noise defined as just this random thing scaled by the sigma. Our output was just the image plus the noise. And we said, remember, you have to worry about the size of the sigma with respect to the range of the image. So if your image is 0 to 255, a sigma of 5 might be plausible. If your image goes 0 to 1, a size of sigma of 5 is not plausible. So you have to worry about how those come together. Now, suppose there was noise in your image and you wanted to remove the noise. How might you think about doing that? Now, I'm sure a bunch of you have suggestions that are kind of similar. Here's the typical one, right? Let me replace the value of each pixel with sort of an average of the pixels around it, okay? So Let's think about what that would look like in 1D. And then we'll go to 2D and we'll talk about why is this the right thing to do or when is this not the right thing to do. All right. So here's our first attempt. So we're going to replace each pixel with an average of the values of the pixel in its neighborhood. And this is referred to as a moving average. So here I have some location here, and I just take the average value and I put it down there. Okay? And then I would move my little what's called window as I take my average and I get a new value and I get another one. And then eventually I would get this new somewhat smoothed version of the original. And it's smooth meaning that we sort of averaged the things locally. All right, look, that was not rocket science. That seemed reasonable. But the important question to ask, really important question to ask, is why was that solution intuitive for you? Why did you say, you know what, I'm going to take a little average in order to get rid of some of the noise? What assumptions are you making about pictures and, by the way, about noise in coming up with that answer? All right, so a little thought we come up with, you're making a couple of key assumptions. The first assumption is that the real value of a pixel is probably similar to the values nearby. Okay? Otherwise, why would I use the pixels nearby in order to try to figure out what my real value was? Okay, that was assumption number one. The other thing that you're assuming, and for those of you who know a little bit about probability and math, etc., you're basically assuming that each noise that's been added to each pixel is independent of the noise that's been added to all the other pixels. And so what that means is if I take the average of the noise, that's going to tend to, I'm going to assume 0. That is that sometimes it'll be up and sometimes it'll be down. And if I take the average around them, that will be 0. So if I have pixels nearby having about the same value or related and the noise is independent, then the average is the right thing to do. So here's a quiz just to sort of keep you on your toes, or at least to keep you mildly awake. If noise is just a function added to an image, we could remove the noise by subtracting that noise again. That is, the operation's reversible. Okay? A. True. Yep, we could do that. B, true, because we don't know the noise function, so we wouldn't know what function to remove. C, false. When you put noise into something, it destroys information in the image, and there is no way to recover it. Well, this is one of these funny things. Well, B is certainly true. Okay? Yes, I could remove the noise if you told me what the noise is, but nobody ever tells you what the noise is, because if they did, they would have removed it in the first place. So you don't know what the noise is, you just know the statistics of the noise. And then, here's one that's interesting. False because additive noise destroys information. Well, if you have just plain addition and the addition works, then that statement is not true, and so C would be wrong. But suppose you have a limit between 0 and 255, or even 0 to 1. If your noise pushes you beyond the limits and you clip, you've lost that information. So sometimes when you add noise, you get these nonlinearities. But in general, we can't remove the noise because we don't know what the noise was. If we did, we could just subtract it. Let's revisit our weighted average, okay? So instead of just thinking about averaging the local pixels, let's think of this as a set of weights, okay? And what we're going to do is we're going to weight all of these pixels by some set of weights, and we're going to combine them using those weights to come up with a new value. Now, when we were just doing the moving box, our weights were just, let's say if it was 5 long, they would be 1/5, 1/5, 1/5, 1/5, 1/5, 5 of them, right? So our weights were uniformly distributed, okay? But wait a minute. Does that make sense? Remember our assumption that nearby pixels are related to my value? And there's another related assumption to that. The more nearby you are, the more related you are. So that means that pixels that are closer to me should contribute more to the average. So let's change our moving average so that that's true. Okay? Before, if you remember, we had these uniform weights, 1, 1, 1, 1, 1, all the way across divided by 5. What if we wanted to use some non-uniform weights? So here's a set, 1, 4, 6, 4, 1 divided by 16. And what I'm going to do is I'm going to change those weights from being uniform to being non-uniform, and I want you to watch what happens to this bottom picture, right? So this is the uniform weight, and that's the non-uniform, center weighted, right? Uniform, non-uniform. And you'll notice that the non-uniform is a smoother rendition. In fact, take a look here